Sir, you may begin. Sir, you may begin.
Thank you very much. Good morning, everyone, or afternoon, depending on where you are calling in from. My name is Gene Amparano with the Federal Highway Administration. This is the second of a series, the 10th of a series of 12 webinars that we started back in June on the Highway Safety Manual. Before we get started, there are a couple of things that I would like to go over. The first thing I would like to draw your attention to is to the poll pod that's in the upper right corner. We at FHWA are trying to keep track of the number of participants that are attending our webinars. It helps us very much in prioritizing our efforts. Below, so if you would kindly select which the number of people in your call-in group, we would greatly appreciate it. Pod directly underneath the poll pod is the HSM webinar series presentations. Here we post copies of all the presentations that we've presented in today's webinar and in previous webinars. We also have the HSM spreadsheets that you can use or have been developed for use with the Highway Safety Manual, and there's 3 of those. The first one's for rural 2-lane roads, the second is for rural multi-lane roads, and the third is for urban and suburban roadways. So feel free to download any of those materials. The third pod located directly below the presentations is the pod that has all of the links to the previous webinars. Pod at the bottom lower right-hand corner is our closed captioning pod. And in that particular pod, if you so desire, you can change the font size by selecting the CC button and then selecting the font menu and then the appropriate font size. Okay. Again, today's webinar is number 10, hour 12. It's going to be on the HSM applications to horizontal curves. It's going to be one session that's going to be presented by John McFadden, the safety engineer with our Resource Center Safety and Design team. And the first part is going to be on introduction to the Highway Safety Manual. So if you've been attending some of the previous webinars, some of this may be repetitive, but we feel that it's important and worth repeating in case we do have some viewers or attendees that haven't seen this material before. And then John's going to be talking about predicting crash frequency and application of the crash modification factors out of the Highway Safety Manual for horizontal curves. And he's also going to present some applicable safety countermeasures for horizontal curves. Questions, we will be taking questions at the end of presentation, John's presentation. There is a chat pod on the lower left, and if you have an urgent question, if you enter the question, we will try to respond. With that, I'm going to go to the presentation room and let John begin his presentation.
Thanks, Gene. Good morning or afternoon, everyone. As Gene mentioned, we are here today to discuss the Highway Safety Manual applications to horizontal curves. My name is John McFadden. I work with the Federal Highway Administration Resource Center Safety and Design Technical Service Team, and I will be presenting this session webinar for today's Highway Safety Manual program. The outcomes for this session include a brief description and some background information on the Highway Safety Manual. Next, I will discuss how crashes at horizontal curves are going to be evaluated using the Highway Safety Manual, and then also look at potential countermeasures to improve safety performance at horizontal curve sites. But with that in mind, let's begin. What is the Highway Safety Manual? For the, I guess, last 30, 35 years, researchers have been interested in understanding the safety implications with design decisions, and this document is a synthesis of much of the research that has been conducted. It provides us with analytical tools for predicting and understanding the impact of our design decisions as it relates to roadway safety performance. It is a large document published by AASHTO that is comprehensive in nature, but I would also state that it is a living document. And what I mean by that is this document will constantly change through time as research is conducted and as we gain a greater understanding as to the implications with our design decisions on safety. The timeline of the Highway Safety Manual development is shown in this slide, and it shows the initiation began back in 1999 at a TRB meeting where there was the identification of a need to estimate safety impacts. I would say or argue that prior to 1999, our field as transportation engineers formed some sort of safety evaluation in the projects we did at some level. The tools as we have now with the safety manual might not have been as organized, but I think that what we provide you with is a synthesis of all the research that has been conducted from early 1999 and earlier up to 2010 with this first edition. And then you can see we've really focused from the 90s to 2000s into understanding explicitly the impact of our design decisions on safety. If you are not familiar with the Highway Safety Manual and you have in the past worked with the Highway Capacity Manual, the format of the Safety Manual is similar to that of the Capacity Manual. And the Safety Manual will, in essence, quantify safety performance in a similar way that the Capacity Manual evaluates the operational performance of a roadway. Why do we need the Highway Safety Manual? Well, I had mentioned it earlier. We're trying now to explicitly have the capability to incorporate safety into the decision-making process. In order to do that, we need to be able to quantify the effects of different design decisions on safety in a similar way as we can quantify the effects of different designs and the impacts they have on the construction cost, the right-of-way, environmental impacts, or operational impacts. The safety manual allows us to do the same for safety in explicitly being able to evaluate potential design alternatives and the impact they have as it relates to the expected number of crashes that are expected at a site. Excuse me. The Highway Safety Manual can be used in a number of ways. It can be used from a screening perspective as it relates to identifying those sites that have the largest potential for crash reduction. It can also be used to identify contributory factors for crashes. It can be used to evaluate different designs that you would consider for a specific project. It can be used also to evaluate from a group of projects which project would you be best served investing in from the safety perspective. When I present topics related to the Highway Safety Manual, I try and use the analogy as we as transportation engineers are now and have been in the business of managing risk. And with budgets being so restrictive at this time and the limitations associated with funding, we need to make the best choice as it relates to investing our safety funds and public monies in order to yield the biggest return on a safety dollar investment. From that perspective, the Highway Safety Manual is a critical tool to be able to differentiate between projects and within a project the best design that will yield the biggest return on our investment. And I think that is at its core the critical benefit that the Highway Safety Manual allows us as transportation professionals to achieve. The Highway Safety Manual is organized in the fashion shown on this slide. In Part A, you have introduction and background information, human factors, and fundamental terminology issues and concepts related to highway safety. Part B, the safety manual discusses road safety management process and specifically gets into what a lot of transportation professionals refer to as the Highway Safety Improvement Program, HSIP process. Part C involves the predictive method. And what this is the part of the manual that allows the user to predict the expected safety performance of a site based on the functional classification of that site and specific ADT and section length characteristics of that site. And then Part D involves accident or crash modification factors. Now, we're focusing today on Part C and Part D with the perspective of, for Part C, the focus of Chapter 10 is two-lane rural roads, Chapter 11, urban, suburban, arterial highways, and Chapter 12, rural multi-lane highways. From the predictive methods perspective of Part C, the focus has been on these facility types for a couple of reasons. Primary reason is when you look at the crash data, you will find that two-lane rurals, multi-lane, urban and suburban highways, and rural multi-lane highways are those with the largest crash problem. When I say crash problem, what I mean is from a two-lane rural perspective, it has the highest fatality rate when compared to the other functional classes. And when I speak of urban, suburban, multi-lane, undivided highways, this has the highest total crash rate and the highest injury crash rate. So a bunch of the research that has been conducted focuses on these facility types. So the initial version of the Highway Safety Manual, you will find that these chapters account for most, if not all, of the material from the predictive methods. And then Part C, the common procedures involve the crash modification factor and calibration for local conditions. We'll also discuss a little bit. In review again from previous webinars, the safety performance function model by definition the site meets a certain set of base conditions, and then we would adjust those base conditions to reflect the prevailing condition using crash modification factors. Broken down into roadway segments, intersections, interchanges, special facilities, and road networks. What a crash modification factor is, it's an adjustment that's used to account what that specific treatment or design attribute, the effect that has on crashes. So for example, if the crash modification factor has a value of 1, you are essentially meeting the base condition. So it has no effect on the expected crash frequency. if the crash modification factor takes a value less than 1, the specific treatment or design attribute reduces the expected crash frequency. And if the crash modification factor takes a value greater than 1, the treatment or design attribute increases the expected crash frequency. How could we use these crash prediction models and procedures? Well, I had mentioned it a little earlier, but it can be used from a couple different perspectives. From a program level, it allows you to look at multiple sites to identify which site will yield the biggest return on a safety investment. So from the perspective solely of safety, it allows you to compare multiple sites to identify which of these sites will yield the biggest return on a safety dollar investment or has the biggest potential for safety improvement. On a project level, it allows you to assess the impact of different designs on a specific project from the perspective of safety. And finally, this Highway Safety Manual and Crash Prediction Evaluation allows you to defend your decisions based purely on the expected safety performance from the design that was selected. The roadway segment prediction model is shown in this slide. And what you see is capital N subscript predicted -RS, which refers to the number of predicted crashes for your roadway segment. And that's a function of, or equal to, the number of crashes that is predicted by the safety performance function, or number N sub SPF for that roadway segment RS. And then you multiply that by crash modification factors, which reflect the prevailing conditions for that roadway segment that we're dealing with. So similar to how, if anybody has used the Highway Capacity Manual, you operate from the ideal condition as it relates to the capacity of a freeway segment, for example, can potentially put through 2,300 passenger cars per hour per lane. With that theoretical knowledge, then you multiply or adjust that to reflect what your prevailing conditions are. We're doing the same type of approach here, where the number of crashes that the safety performance function predicts is based on a set of base conditions, or you could also call ideal conditions, that we'll get to in a minute. And then we multiply that by the crash modification factors for the prevailing attributes, be they design attributes or any other treatments that we have the knowledge as it relates to the impact on crashes. We multiply those by that base number or of crashes predicted by the safety performance function for that roadway segment. And then the last term is a calibration factor. And what that allows us to do is to adjust this national model to reflect the local conditions using crash data that we have locally. So if we were to apply this, you'll notice in this example, the number of crashes that we're predicting are based on this safety performance function. And this safety performance function is, in its very simplest form, just a crash model. It's telling you how many crashes are going to occur on a two-lane rural highway based on the section length in miles and the ADT that you have on that two-lane rural highway. With that information, if you plug it in, you can yield for any two-lane rural highway the expected number of crashes that you would have given that ADT and section length, assuming that that two-lane rural highway met the base conditions. What are the base conditions? Well, we get to them now. They include a lane width of 12 feet, a shoulder width of 6 feet. The shoulder type is a paved shoulder. a roadside hazard rating of 3. This roadside hazard rating is a somewhat subjective, somewhat objective measure of the roadside characteristics. The objective part of this roadside hazard rating is that it's a function of the clear zone and the side slopes that exist for your roadway. So, for example, a roadside hazard rating values range between 1 and 7, with the value of 1 corresponding to a clear zone of 30 or more feet and a side slope of 2 to 1 or steeper, and a value of 7 corresponding to a clear zone of less than 5, or excuse me, clear zone of 1, or excuse me, a roadside hazard rating of 1 corresponds to a clear zone of less than 5 feet, side slopes 2 to 1 or steeper. Roadside hazard rating of 7 corresponds to a clear zone of 30 or more feet, a side slope of 5 to 1 or flatter. And then 2, 3, 4, 5, and 6 break up into a matrix with adjustments reflecting side slope and clear zone values that vary. So we're somewhere in the middle. The roadside hazard rating of 3 corresponds to a clear zone of about 10 feet and side slopes of 3 to 1 or steeper. Driveway density, base condition is 5 driveways per mile. We are on a flat grade there, and that's plus or minus 2%. And we are on a tangent section of highway, which is the focus of this workshop. How do we incorporate horizontal curvature into the highway safety manual? There are no vertical curves in the base condition, no centerline rumble strips, no two-way left turn lanes, climbing or passing lanes, no lighting, no automated enforcement. Now, at this time, I typically ask, when I'm teaching this class in person, do these attributes reflect all of the possible factors that when you go to a roadway have an impact on safety? And the answer to that is no. What these do reflect, though, is the factors that we have the understanding from a statistical perspective as to what impact these attributes have as it relates to safety, or number of crashes. So that's why we have a crash modification factor associated with each of these attributes. So were your 2-lane rural highway to have all of the corresponding base conditions, then if we go back to that example, or forward to an example where we have 3,580 vehicles per day and a 5.02 mile section, and we plug it into that SPF, we would expect to have 4.69 crashes per year on that section, a 5-mile section of 2-lane rural highway. This assumes that that 5-mile section highway has the base conditions described in the previous slides. Okay. That concludes the background information related to the Highway Safety Manual. At this point, I'm going to now direct my attention towards how does the Highway Safety Manual address horizontal curve crashes. And why is it necessary to evaluate horizontal curve crashes? Well, if we look at the safety performance on horizontal curves, we find that 28% of all fatal crashes occurred at horizontal curves. And this resulted in 11,436 deaths. 69% of these were rural, 71% on roads classified as minor, arterials, or below. So when we look at the data, the average crash rate for horizontal curves is approximately 3 times that of tangent sections. This slide illustrates the problem of horizontal curve crashes when we look at the frequency of horizontal curve fatal crashes for the 3-year period, 2006, 2007, 2008, the average number per year. And again, this is the percent of the fatal crashes that were horizontal curve fatal crashes for that same time frame. So the darker the state color, the higher the percentage of horizontal curve fatal crashes. When we take it a little further and look at diagnostic measures of horizontal curves, what we're finding is from the research that once you get a horizontal curve with a radius of greater than 2,000 feet, it is performing very close to that of a tangent section. So in investigating safety at horizontal curves, some states have isolated those sites that have horizontal curves with curve radius less than 2,000, and some focused even more more intently at sites or horizontal curves with radius less than 1,000 foot radius to identify those sites that were experiencing the highest crash problem. That's illustrated in this slide that is based on research by Bonison and Fitzpatrick. You get below that. The horizontal curve terminology that we're describing here, for those that are not familiar, is the curve radius there's direct, I guess, an inverse relationship between the degree of curve that we would see and the horizontal curve radius that that is shown in this slide. Horizontal curves are designed is based on driver comfort. Now, additionally, the model is shown in this slide, which basically the left side of the model is the superelevation, and the design side friction factor is offsets the design speed divided by 15 times the curve radius. This AASHTO model assumes a few things. First, that the driver in the car tracks the curve as a point mass, and that the driver operates at a constant speed through the curve. And then finally, that the curve design avoids loss of control due to skidding. And it's been hypothesized in the research that these assumptions are often violated. And I can attest to this as I have driven to go closer to the inside of my travel lane so that I can maintain a higher speed through the loop ramp and off track through the curve. Well, what I'm doing there, in essence, violates the first two assumptions that are shown in this slide. By off tracking through a horizontal curve, we are not tracking the curve as a point mass, and by changing speed within the limits of the curve, we are violating the assumption that we traverse the horizontal curve from PC to PT at this slide that's shown illustrates some of the safety problems with horizontal curves, and basically documents that there's a 3 times more likely to have a crash on a horizontal curve when compared to a tangent section. That's from Glennon's research. The AASHTO model is independent of traffic volumes, functional class, vehicle mix, And as I described before, um, the assumptions from that model are violated based on our driver performance. We as drivers traverse horizontal curves more as like a spiral than we do an actual constant radius and constant speed. And research following up investigating the implications of the difference between the astro model and how we actually drive these curves, it shows that what's occurring is we are much more aggressive, especially on lower design speed horizontal curves than the curve is intended. And what's being shown here is um, the fact that we are overshooting the path of the curve, we're driving it as a spiral, and we are doing it independent of speed. And this slide illustrates the fact that, for example, a 1,000-foot radius curve is driven by the 95th percentile driver as though it were a 700-foot radius curve at some point within the limits of the curve. And what that's saying is what the example I described earlier, that we will maintain a higher speed as we enter the curve until we get to a point where we're uncomfortable enough where we're forced to make that sharper turning radius. And in this case, for a 1,000-foot radius, we actually traverse the curve at some point within the limits of that horizontal curve as though it were a 700-foot radius horizontal curve. So with that in mind, what we're seeing in this slide is the relationship between the inferred design speed and the actual 85th percentile speed on horizontal curves. The problem area associated with this slide is the sites or the dots that are above that 45-degree line. Those are the horizontal curves where our 85th percentile speeds are above the inferred design speed for that horizontal curve. And that is consistent with what we're seeing from that earlier slide where those horizontal curves with a curve radius of 1,000 feet or less were the curves where the crash rates were geometrically higher than that for the curves with 1,000 feet radius or more. So there you're seeing the above that 45-degree line, the curves are driven faster than the policy assumption. Below that 45-degree line, the curves are driven slower than the policy assumption. And the curves below that 45-degree line are typically those on higher functional class facilities. Curves above that 45-degree line are typically the lower functional class. The facilities that are on the above were operating at a higher speed than the design speed of that facility. Excuse me. So how do we assess the risk of a horizontal curve? One such metric that we can use is operating speed models. And what this does is it gives us a metric as to is our design consistent or not. And what do we mean by consistent design? I'm referring to a design that meets the driver's expectations. So in attempting to meet the driver's expectation, one metric we use is evaluating speed differentials between successive design elements. So in this case, we're looking at the 85th percentile speed from a approach tangent to a horizontal curve, and then comparing that. Another way from this case is looking at the 85th percentile speed and subtracting from it the design speed for that horizontal curve. Either of those two metrics can be used to assess the risk associated with that curve or the amount of inconsistency of that curve when compared to driver's expectations. When you have a delta of that operating versus design speed of greater than 20 kilometers per hour, you're in a high-risk zone and corresponds to greater than 12 miles per hour. You would want to evaluate some sort of treatment to alert drivers that there is in this case, a horizontal curve that is approaching that violates their expectations. And then in the case where you're having between a 6 to 12 mile an hour reduction in speeds or difference in speeds between the 85th percentile operating speed and the design speed for that curve, there's a cautionary point there where you'd want to alert drivers that this may be a condition that violates their expectations. Okay. We've covered crash modification factors, and we bring it up again in this point because we are about to illustrate how the Highway Safety Manual attempts to quantify the safety effect of horizontal curve based on the specific geometric design attributes of that horizontal curve and placing it in terms of a crash modification factor. So, and the modification factor quantifies this expected change in crash based on the treatment, and the treatment in this case is the horizontal curve. So what this model, which takes into account the length of the horizontal curve in miles, the radius of the horizontal curve, and whether or not spirals are present. The crash modification factor for any horizontal curve then can be developed based on the geometric design attributes of that curve. The inputs shown here are pretty direct. What you do is take your length of curve in miles, your radius of curve in feet, and spiral is a dummy variable. If a spiral transition exists, you put a value of 1. If it does not exist, you put a value of 0. Plug it in and you would obtain the crash modification factor for the horizontal curve that you are dealing with. So if we apply this to an example, and we look at a horizontal curve with a length of 480 feet, which corresponds to 0.091 miles. We have a curve radius of 350 feet, no spiral transition, and we threw in the central angle there of 78.6 degrees. We then plug it into the equation, putting the values in, and you would get a crash modification factor of 2.62. What does this mean? This means you would expect 2.62 times more crashes at this site when you compare it to the same exact site as though it were a tangent section. And that's the critical feature associated with these crash modification factors. They are used as a comparative measure when you're comparing what treatment or physical geometric design attribute you have on site. When you look at that, the effect that that attribute has when compared to the base condition. So in this case, we would expect 2.62 times more crashes at this site when compared to the same site as though it were a horizontal tangent section of roadway. There is another CMF that exists also at horizontal curves for superelevation. And the way that the safety manual incorporates the effect of superelevation on safety is through a crash modification function here. So what they first describe is superelevation variance. And what that term means is it's the difference between what the superelevation that exists on site at your horizontal curve is when compared to the AASHTO or state standard or allowable superelevation for that site. So if the superelevation variance or difference between the state allowable or AASHTO Green Book allowable superelevation and the superelevation at that site is less than 0.01, then the crash modification factor for superelevation becomes 1, or that is the base condition. If the superelevation difference or variance is 0.01 up to, but less, or excuse me, from 0.01 to 0.01999, you would use this function where you would take 1 plus 6 times whatever that superelevation variance is, subtract from a 0.01, and you would obtain your CMF for that superelevation variance. If the superelevation variance is greater than 0.02, you would take 1.06 and add to it 3 times that superelevation variance subtracted by 0.02 as shown in this slide. So if we looked at an example where your design superelevation is 4%, your actual superelevation is 2%, you would fall into that second condition, or excuse me, the third condition, and you would yield a crash modification factor associated with that superelevation variance of 0.02. When you plug it into that third equation, you would get a crash modification factor of 1.06. What does that mean? That means for this site, which is experiencing a 2% variance or difference between the allowable superelevation and what is actually on site, you would expect 6% more total crashes at that site when compared to the same site that had the full superelevation allowable, or the design superelevation. Okay, those two features are how the Highway Safety Manual quantifies the effect of horizontal curves and superelevation on in its procedures. At this point, what I want to do is look at other treatments that can be applied to sites horizontal curve sites, and the procedures that we would take to address some of the safety inadequacies associated with these sites. And this would start with some sort of diagnostic review where you're looking at crash data, talking to law enforcement, maintenance crews, performing safety audits to attempt to identify whether or not your site is operating at an acceptable level of risk or an unacceptable level of risk. Then, if we've identified a set of sites that are operating at an unacceptable level of risk, we can then look for tools to address this problem. One source to address it is through the AASHTO Strategic Highway Safety Plan, and that plan includes 22 emphasis areas, one of which is horizontal curves. The 22 emphasis areas and focus area on horizontal curve is shown here on the NCHRP 500 report series, volume 7, where the topic is reducing collisions on horizontal curves. These 500 series guidebooks are available free of charge, and you're able to download those on the internet. I would encourage you to, under any search engine, type in 500 series, NCHRP 500 series guidebooks, and it will take you to this link that allows you to download all the material from those guidebooks. Federal Highway Administration has also published a series of reports and workbooks related to low-cost treatments for, in this case, horizontal curve safety. And this is also available free of charge for download. Now, within those guidebooks are a set of treatments, and depending upon um, the types of crashes and um, other data related to your specific sites, it will lead you into potential treatments that may be more appropriate than others for your improving the safety at your site. Well, a couple metrics that you can look at, as we discussed earlier, the difference in the approach speed to the curve speed, geometric characteristics of the curve, your sight distance around the curve, unexpected features associated with the curve, if you have intersections or change in the curve radius within the curve, traffic volumes, your roadside environment, right-of-way conditions. But from a very broad perspective, the first recommendation, assuming there are no unusual attributes associated with your site, is attending to the basics. And what we're doing here is for conditions at that site that don't meet driver expectations, we would want to upgrade them to make them meet driver expectations, specifically related to traffic control devices on site, so signs, signals, and markings, ensuring that they are compliance with the MUTCD and alerting drivers to any unexpected conditions that are presented with this site that would violate driver expectations. So for example, we want to make sure we have longitudinal pavement markings, where warranted have horizontal alignment signs, speed advisory plaques, or combination of the alignment and advisory placard signs, delineators, chevrons, and this slide illustrates a 4 to 6 inch yellow stripe pattern, edge line markings, and ensuring that the sites that require your edge line markings include them. Here are some of the horizontal alignment signs taken from the MUTCD. And what we're trying to do here is, again, alert drivers to changes in the alignment using the tools that are available to us in the MUTCD. The MUTCD has just adopted some new warrants for when you would install the advisory horizontal curve advisory sign and the speed advisory placard as a function of the speed difference from the approach tangent to the horizontal curve. So I would also encourage you to make sure that we incorporate that warrant into the decision-making process for application of the signs, signals, and markings as appropriate. Here's the case for using the curve symbol sign, not the legal speed limit sign in this case, and this is based on engineering practices, where we're posting the advisory speed versus the posted speed for a speed differential that exists on site. What you will see also in the Part D of the Highway Safety Manual are for specific treatments, in this case the installation of the horizontal alignment speed advisory placard. You will have an effect of that application or treatment on safety, as identified here. There is an AMF associated with that installation of the horizontal alignment speed advisory placard based on the setting type, traffic volume that are shown there. In this case, they're unspecified. Future research will update that and adjust to reflect for the different possible roadway types and traffic volume conditions the effect of that treatment. And then on the crash type by severity, the adjustment to the expected number of crashes using this CMF. Delineators are another treatment that help show curve alignment through retroreflectivity, mostly at night or under adverse weather. We use them on the outside or both sides of the road, and also consider chevrons when you have a crash history. And this slide illustrates the visual effect that these chevrons can help with when you see the approach to a horizontal curve here to the left from the before to the after stage at this site. And it provides a visual cue And the true, or I guess major benefit is not in daylight conditions. It'd be more pronounced in the evening or in darker conditions. Then when you've met standard and you still are experiencing a safety problem at a site, at this point you have to go beyond the standard type of bells and whistles or tools that are available to us from the MUTCD to really accentuate to the driver there is something that you're not expecting that's coming up down the road. From the focus of this presentation, we're dealing with horizontal curves, so you might need larger signs or doubling up of the signs or higher grade retroreflective materials to really shout out to the driver, there's a horizontal curve ahead that you, under normal circumstances, wouldn't be expecting, but because of the specific unique nature of this location, we couldn't put in the curve that you're expecting, so you need to really adjust your driving behavior and slow down in advance of this curve. And it's incumbent upon us to do whatever is necessary to alert the driver to this condition that is inconsistent with what their expectations are. And these are some of the enhancements that we could make, including yellow sign sheeting, flashing beacons, profile pavement markings, RPMs. And there's an example of doubling up the signs, and there's also a flashing beacon on the sign to the right. There's fluorescent yellow chevrons versus your standard yellow chevrons, and you can see they're a little more pronounced in this image, those fluorescent yellow chevrons. The flashing beacons are shown in this slide. Profile pavement markings, raised and inverted, are shown, and these are made of snowplow resistant thermoplastic, creates a rumble effect and it has enhanced visibility. There's the retroreflective raised pavement markings, which improves the visibility distance on the roadway alignment, and it's best in wet weather and at nighttime. Retroreflective barrier delineation, and this is showing a concrete barrier rail or metal guardrail. Putting that retroreflective delineation is also a way to provide information to the drivers as they approach, especially at night, changes in the alignment. And that's an example at a horizontal curve of the use of that retroreflective barrier delineation, along with some other treatments that we were previously discussing. Dynamic curve warning systems are also, and now we're talking about higher end and a little more costly devices to really shout out to the drivers, there's something coming up that you might not be expecting. In-lane pavement markings are another tool that can be used to warn the drivers of a horizontal curve, in this case the advisory speed for that curve. Shoulder rumble strips are also a tool that can be used to alert drivers to keep them on the roadway, especially around horizontal curves. I go over some of these issues. The next webinar will discuss a lot of the attributes I've just discussed in more depth. This is the roadway departure webinar that is going to be mentioned by Jean at the end of this presentation. I believe it's on the 27th of July. They'll be discussing the highway safety manual from the perspective of roadway departure crashes. And rumble strips will be covered in that workshop as well. And then centerline rumble strips are another tool that can be helpful to prevent crossover crashes at horizontal curves. Minor roadway improvements where we're doing low-cost physical changes to the roadway, including skid-resistant pavements, eliminating edge drop-offs through safety edge, or widening shoulders on curves, are other ways to influence or improve safety at these locations. And the skid-resistant pavement surfaces include pavement grooving, which involves longitudinal directional vehicle control improvements by milling in 3/16 to 3/8 inch wide cracks or uh, indents indents into the pavement versus a skid-resistant application where you have epoxy-based material along with an aggregate to improve the surface friction of the roadway. This slide illustrates a widened shoulder on the outside of curve to provide an increased factor of safety for a driver to leave the roadway to recover and get back on the roadway. And this slide illustrates the effects of widening the shoulder in reducing related crash types based on the type of shoulder. And the safety manual does provide specific crash modification factors for the shoulder width by type that you will and have, if you've seen the previous webinar, been able to use. Then there are also maintenance treatments, restriping markings, replacing signs or upgrading the sheeting, controlling overgrown foliage, maintaining your shoulders, eliminating obstacles, and improving drainage will also yield a safety benefit. Replacing signs, sign visibility deteriorates over time due to fading and loss of retroreflectivity. And we have minimum standards now for signs that we will want to achieve. Cutting back foliage will improve sight distance and sign visibility and will have a direct impact on safety. And at the end of the day, we will always encourage delineation when you have limitations as it relates to budget or other factors that would influence your ability to relocate, remove obstacles. At the very least, I think we can delineate. So in this webinar, what we did was describe the Highway Safety Manual, discuss how crashes at horizontal curves are evaluated in the Highway Safety Manual, and then looked at a few different countermeasures to improve performance from the perspective of safety at horizontal curves. This time I will field any questions. I'll turn it back over to Gene to open up a forum to discuss any comments or questions related to horizontal curves, the Highway Safety Manual, or any countermeasures that were discussed.
Okay, thanks, John. Jerry, can you open up the lines for questions?
Certainly. If you would like to ask a question or make a comment, please press *1, unmute your phone, and record your name. To withdraw your question, press *2. Once again, to make a comment or ask a question, please press *1, unmute your phone, and record your name. One moment.
John, we have several questions in the chat pods while we're waiting for verbal questions over the line. Perhaps we can, I tried to address those that I could, but perhaps I wasn't able to address all of them. So if you see something there in the chat pod that needs to be addressed, take a look at that, John.
Yeah, I'm looking through them now.
And right at the moment while you're checking that, we have no questions on the audio.
Okay. We received a lot of questions regarding why isn't there a CMF for different things, such as pavement surface and some other items. We have to remember that this is just the first edition of the Highway Safety Manual, and as John mentioned in his presentation, that this is considered as a living document, so we expect changes to occur as more research becomes available. There are some gaps in the Highway Safety Manual. It's not perfect. It doesn't cover everything, and the researchers and the developers of the Highway Safety Manual are fully aware of that. As a matter of fact, they've already established a TRB committee to try to identify those gaps and fill those gaps in the future edition of a Highway Safety Manual. And one of the things that they've asked us to do as presenters of the Highway Safety Manual is for us to track some of the questions, the common questions that participants of the workshops and attendees of these webinars as what they see as missing items in the Highway Safety Manual and bring it to their attention, and that's what we're trying to do. And so things like this that show up in the chat pod asking why a certain CMF, or if there is a certain CMF for a certain application, we are recording that, and there is a TRB committee that's meeting, the one on the safety performance of the Highway Safety Manual in August, and we're going to bring some of these items to the table at that meeting, share it with them. We have a question from Ed Kennedy asking, is there a methodology where it says it's time for geometric upgrades like changing a radius? There's nothing in the Highway Safety Manual that talks about changing the radius. What can be done is by using the crash modification function that John showed earlier on horizontal curves, you can calculate the effect of a certain radius. So if you have some curves with substandard radii, you can calculate the CMF and determine how that particular roadway is behaving. And I would say that if it's not behaving properly, then perhaps it is time for a geometric upgrade.
And Gene, I'm reading through here and I see there's a question related to CMFs and whether they exist for example, pavement safety edges, for bots, dots, or RPMs, I guess is what they're referring to there, for raised pavement markings, side friction factors, and pavement surface improvements. And the material that I presented, it illustrates to date the CMFs that we have available to us related to understanding the effects of the horizontal curve on safety performance. There are some, you may bring up a lot of good questions, and when I present this publicly, I often go out and say, for every one problem we solve, 10 more questions come out related to, well, how does this feature influence safety? So it's almost a researcher's dream, this Highway Safety Manual, as it relates to the fact that you're basically creating an infinite amount of research questions when you try and truly understand the impacts of our design decisions on every possible design that we would deal with from a transportation professional. So I hear your message, and what I would say to you is that there is a warehouse of crash modification factors that Fed Highway has online that is constantly updated. And even if you purchase that hard edition of the Highway Safety Manual, it is going to refer you to this site to constantly make sure that you are aware of the new crash modification factors that come out, because they come out and will continuously come out over the next few, well, I guess from the perspective of what we do, indefinitely, until we've figured out the majority of how the variability in crashes are influenced by our design decisions. We're going to continuously investigate how these attributes impact crash. So I encourage you to go to the Fed Highway warehouse on crash modification factors.
Do you know the website for that?
I don't have it at the top of my head, but if you type in FHWA CMF warehouse, it will, into any search engine, it will link you there. Give me a second, I could look it up myself.
Are there any more questions?
Once again, if you would like to make a comment or ask a question, please press star 1.
Karen has entered the web link to the clearinghouse, CMF clearinghouse that John was referring to. Thank you, Karen. Neil from New York's DOT says it'd be nice if there was a software that updated itself. Yes, that would be nice. Fortunately, that It has to be done manually. In Palmer asks, do you foresee a factor for pleasure routes, commuter routes, commercial corridors, recreation routes? That's a hard question. I don't know the answer. It's possible, but we've got to remember that all the CMFs and the safety performance functions are developed on research, or they come out of research. So unless there's a lot of research going on in those areas, then it's likely that it won't show up in the Highway Safety Manual. I'm just reviewing something that just popped up. It talks about horizontal sight distance, a major factor to provide minimum stop sight distance and reduce crashes. Yes, minimum sight distance and stopping sight distance is critical in roadway design. However, we don't have any crash modification factors associated with sight distance. There's also a question concerning a combination of vertical and horizontal curves for predicted crashes. Don't recall seeing that question, but there's no crash modification factors for vertical curves per se, but there are crash modification factors for roadway segments on grades, and those are listed in the Highway Safety Manual. Those are for two-lane rural roads. So that was covered in a previous webinar. If you didn't get a chance to participate in that webinar, when we go to the wrap-up room, there are the links shown in a pod on the right where you can go to those particular web links and click on them, and they'll take you to the recorded version of that particular webinar. You can view it. Any more questions?
At this time, we have no questions on the audio.
One final question popped up to the presenters. Does the coefficient of side friction related to pavement surface affect a crash modification factor? John, you want to try to answer that one?
Yeah, that's from the perspective of the equation, or are they asking, is there a separate crash modification factor that focuses strictly on?
I guess he's asking, does the side friction, is that built into the CFM?
Well, it's an interesting question. Yeah.
From the equation.
There is going to be, I guess, confounding effects that are occurring here when you think about how these crash modification factors were calculated. We went out, we being the transportation research community, and looked at safety performance at horizontal curves. Well, one of the challenges that we have in trying to understand the safety effects of the different geometric design attributes is we're limited to what's built out there. So when the question comes up, does the coefficient of side friction related to pavement surface affect the CMF? It not explicitly, but the horizontal curve was designed based on some coefficient of side friction factor. When we use the highway safety or the AASHTO design model to generate that. So for me to say explicitly, do we use that as a term to calculate the CMF? No, but implicitly, is it included or was it included when you developed the CMF? I would argue yes, it was. And this is what Gene was mentioning earlier, and I'll follow up on it. At this point, with the first version of the Highway Safety Manual, we are really, the transportation research community has attempted to isolate specific independent design elements and understand what changes to those specific design elements have on safety. Now, what I envision future generations of the safety manual will do, it will almost as though it become a multi-dimensional matrix where you're starting to understand the implication of multiple changes and what impact that will have uh, on safety. But at this point, we are focusing in strictly on the effects of changing one specific design element. So I see the follow-up question. If you resurface the horizontal curve with a good pavement or not, dry or wet, can affect the value of F, although the horizontal curve exists. Um, and gee, I'm trying to digest that. Yeah, and the improvement in another workshop from our team's perspective, we are encouraging at locations, horizontal curve locations, the use of high friction pavement enhancers. So, and we have found that there has been uh, an impact on reducing crashes at these horizontal curves when you improve friction at these locations. So yes, I can say that there is a trend that shows there's an improvement to safety. It hasn't been quantified yet to a CMF.
And I think that's the key there. It just hasn't been, a CMF has not been developed for pavement friction, surface friction, but that doesn't mean it won't come to surface in a future edition of the Highway Safety Manual. As a matter of fact, in my opinion, it will be available at some time in the future.
Yeah, and the next question was in all weather. I would say yes, wet weather, you've seen more pronounced effect. As long as the pavement and the tire have an interface, you are seeing the effect of that enhanced pavement friction. The impact on safety exists. Once you get snow and ice, then you're not going to see that effect because the pavement tire interface does not exist.
Excuse me, gentlemen, we do have a question on the audio. Would you like to take that one now?
Yeah.
Okay, and that question is from Tim Simademas. Your line is open, Tim.
Hi, thank you. Now, these CMS are related, show you what you'd expect the difference to be to a straight tangent section. So if you're looking at an existing curve and reconstructing and flattening that curve, is it as easy as just comparing your existing condition CMF to the proposed condition CMF and taking the difference and then using that for an expected change in your crashes, or is there more to it than that?
That's exactly how I would deal with it. You're basically doing a comparison of what exists, what your proposed changes would be, and quantifying the safety effect of that through the CMFs and the safety performance function.
Okay, thank you.
And at this time, we have no further questions on the audio.
I don't see any further questions in the chat pod either. So if there are no further questions, we will conclude the presentation. I'm going to the wrap-up room. Our next webinar is webinar number 11 out of 12, and it's going to be applications to roadway departure crashes, July 27th, 1:30 to 3:30 p.m. Eastern Time. Again, on the upper right corner are the links to the recorded sessions. So if there's any sessions, they're listed by date and title with the link. So if there's any session that you weren't able to participate on, you can go and view the recorded session by clicking on the link. Also, we have copies of the presentations from today's webinar that John presented, and also previous webinars in the pod labeled HSM Webinar Series